December 21st, 2019. 3:47 a.m. Eastern Time. The Canadian Hydrogen Intensity Mapping Experiment, CHIME, a massive radio telescope in British Columbia, picks up something impossible. A radio signal from deep space, but not the typical millisecond flash astronomers have been detecting for over a decade. This signal lasts 3 seconds, 1,000 times longer than any fast radio burst ever recorded. And within those 3 seconds, the telescope detects something that makes MIT astronomer Daniele Micili stop breathing. Periodic peaks, remarkably precise, repeating every 0.2 seconds. Boom, 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 like a heartbeat. A heartbeat from a galaxy billions of light-years away. More than 1,000,000 times brighter than any pulsar or magnetar in our own Milky Way. Pulsing with mathematical precision that shouldn't exist in nature. There are not many things in the universe that emit strictly periodic signals, Micili would later say. Radio pulsars do it, magnetars do it, but they're in our galaxy. They're dim, predictable. This signal, designated FRB 20191221A, was coming from cosmological distances, and it was screaming. The question isn't just what could produce a signal like this. The question is, why would it? Because in all of physics, there are very few natural processes that create perfect periodicity over cosmological timescales. Rotation, orbit, oscillation, that's it. And every one of those explanations breaks down when you look at the numbers. This is something else, something we've never seen before. And it's sending a message we don't yet understand. Let me show you what radio signals from space should look like. Since 2007, when Australian astronomer Duncan Lorimer discovered the first fast radio burst, FRB, astronomers have detected over 4,000 of these cosmic flashes. Most last just a few milliseconds, a blink. They release as much energy in that millisecond as our sun produces in 10,000 years. Then they vanish. The vast majority are one-offs. They flash once and never repeat. We detect them purely by accident. CHIME sweeps the sky as Earth rotates, and occasionally, a radio telescope happens to be pointing in the right direction at the exact millisecond when an FRB erupts. The odds of catching one are astronomically small, but about 10% of FRBs repeat. They flash multiple times from the same location in space. In 2015, astronomers discovered FRB 121102, the first confirmed repeater. It flashed irregularly over months and years, sometimes going silent for weeks before erupting with dozens of bursts in a single day. In 2020, a team discovered something even stranger. FRB 180916.J0158+65 showed periodic activity. Not in the signal itself, but in when it appeared. 4 days of random bursts, then 67 days of silence, then 4 days of bursts again. The cycle repeated every 157 days with remarkable consistency. This suggested something was orbiting, maybe a neutron star in a binary system with a massive companion. When the neutron star passed behind its partner, the signal was blocked. When it emerged, we saw bursts. The pattern made sense. This is where things get strange. Because FRB 20191221A isn't like that. The periodicity isn't in when the signal appears, it's in the signal itself. The radio waves repeat every 217 milliseconds, just over 5 times per second, with precision that rivals atomic clocks. For 3 full seconds, the pattern never wavers. Boom, 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 boom. 14 pulses total. Then silence. Before I reveal what astrophysicists think could produce this, and why some of them are quietly terrified, if you want to stay ahead of discoveries happening at the edges of known physics, hit that subscribe button. We're covering real-time detections from telescopes scanning deep space, and what I'm about to explain about neutron star physics and the March 2025 brightest flash of all time will change how you think about what's possible in the universe. Let's go back to the beginning. CHIME isn't like traditional radio telescopes. It's an interferometric array. 4 massive cylindrical reflectors, each 100 meters long and 20 meters wide, aligned north-south in the Okanagan Valley. As Earth rotates, CHIME's field of view sweeps across the entire northern sky once per day. It's designed to map hydrogen in the early universe, but it turned out to be perfect for detecting fast radio bursts. The telescope began operations in 2018. Within months, it was detecting FRBs at an unprecedented rate, dozens per month, then hundreds. Mission Control developed algorithms to identify bursts in real time, filtering out terrestrial interference from cell phones, satellites, and electrical equipment. When a candidate burst triggers the system, the data is flagged for human review. On December 21, 2019, the system flagged something unusual. Daniele Micheli, who was monitoring incoming data at McGill University, pulled up the signal and froze. See, it was unusual, he recalls. Not only was it very long, lasting about 3 seconds, but there were periodic peaks that were remarkably precise, emitting every fraction of a second like a heartbeat. This is the first time the signal itself is periodic. The team immediately began analysis. First step, confirm it wasn't terrestrial interference. They checked satellite data. No spacecraft was broadcasting on these frequencies at that exact time. They checked for solar radio bursts. Nothing. They checked other telescopes. None reported simultaneous signals. The dispersion measure, how much the signal had been scattered by charged particles between here and the source, was far too high to be coming from anything in the Milky Way. This was extragalactic, billions of light-years away. Next, they analyzed the pattern of 14 distinct pulses over 3 seconds, each pulse lasting about 30 milliseconds, separated by 217 milliseconds of silence. The precision was unsettling. Natural astrophysical sources don't usually work like metronomes. Neutron stars, the dense remnants of dead massive stars, can produce periodic signals through rotation. As they spin, beams of radio waves sweep across space like a lighthouse. If Earth happens to be in the path of that beam, we see a pulse. These are pulsars. The fastest spinning pulsars rotate about 700 times per second. Their pulses come every 1.4 milliseconds. FRB 201912221A's pulses are much slower, 1 every 217 milliseconds, or about 4.6 times per second. That's consistent with a neutron star rotating once every 0.2 seconds. Perfectly plausible. But there's a problem. Radio pulsars in our galaxy emit about 10 to the power of 30 ergs per second, a modest amount of energy. FRB 201912221A released about 10 to the power of 38 ergs per second, more than 1 million times brighter. And it did this continuously for 3 full seconds, pumping out 10 to the power of 39 ergs total. That's the energy output of the Sun for an entire week, compressed into 3 seconds, beamed in our direction as radio waves. What could do that? The team looked at magnetars, neutron stars with magnetic fields 1,000 trillion times stronger than Earth's. These objects occasionally produce giant flares, bursts of X-rays and gamma rays as magnetic field lines snap and reconnect. Some theories suggest magnetars could also produce radio bursts during these flares. But even the most powerful magnetar flares don't match FRB 20191221A's energy output. And so the team proposed a hypothesis. Maybe this was a neutron star, either a pulsar or magnetar, that for some unknown reason temporarily became vastly more energetic than normal. Maybe magnetic reconnection triggered a cascade. Maybe the star's crust cracked, releasing stored energy. Maybe something unknown to physics happened in that 3-second window, ejecting a brilliant train of radio pulses. And CHIME was positioned perfectly to catch it. The paper was published in Nature in July 2022. The astronomy community was stunned. Here was direct observational evidence of a new class of astrophysical phenomenon. But the mystery deepened when researchers checked CHIME's archives. Had this source flashed before? Had it flashed since? They scanned 7 years of data. Nothing. FRB 201912221A appeared exactly once, then went silent, and it hasn't been detected again. Which raises a disturbing question. Was this a one-time event? Some catastrophic stellar death? Or does this source flash every few years, and we just haven't been watching long enough to see the next burst? Then, on March 16, 2025, everything changed. At 5:23 p.m. Pacific Time, CHIME detected another fast radio burst. But this one was different. This one was so bright it nearly overwhelmed the telescope's receivers. The signal, designated FRB 202503116A, but quickly nicknamed RB Float for Radio Brightest Flash of All Time, released as much energy as the sun produces in 4 days, in less than a single second. And thanks to CHIME's new outrigger telescopes, 3 smaller arrays positioned across North America to triangulate burst locations with precision, astronomers pinpointed the source to NGC 4141, a spiral galaxy in Ursa Major, 130 million light-years away, relatively close by cosmological standards. And crucially, this burst didn't repeat. It flashed once, brilliantly, impossibly, then nothing. The team turned the James Webb Space Telescope toward NGC 4141 within hours. They imaged the region in infrared and found something, a faint point source of light, right where the radio burst originated. A stellar remnant, or something. The first time anyone has directly imaged the environment of a fast radio burst outside our galaxy. But here's the twist that changes everything. CHIME had been observing that exact region every single day for 7 years. Every rotation of Earth brought NGC 4141 into CHIME's field of view. Thousands of observations, 0 bursts. Until March 16th, when suddenly, with no warning, the brightest radio flash of all time erupted. What could cause this? If FRBs are repeaters, neutron stars that flash periodically, why would one go silent for 7 years and then produce a record-breaking burst? And if they're one-offs, cataclysmic collisions or some kind of stellar explosion, why do sources like FRB 121102 repeat hundreds of times? There's a growing suspicion among astronomers. Maybe there are 2 completely different types of fast radio bursts. Repeaters, which are probably magnetars or pulsars undergoing some kind of periodic activity. And one-offs, which might be something else entirely. Something more violent, more explosive. Something that destroys its source in the process of creating the burst. Theories for one-offs include neutron star collisions, black hole formation events, or even failed supernovas, where a massive star's core collapses directly into a black hole without exploding, releasing a final burst of electromagnetic radiation as the event horizon forms. But there's a third possibility, one that astronomers discuss in careful, measured tones at conferences but rarely write about in papers. What if some of these signals aren't natural? The SETI community, the search for extraterrestrial intelligence, has long searched for narrow-band radio signals from space. The logic: a natural astrophysical source broadcasts across a wide range of frequencies. An artificial transmitter would focus energy into a specific frequency channel to maximize signal strength. Therefore, if you detect a narrow-band signal, it might be technological. Fast radio bursts are broadband. They span a huge range of radio frequencies. This suggests natural sources. But FRB 201912221A's periodicity is troubling. Perfect mathematical precision over 3 seconds. 14 pulses with identical spacing. No drift, no variation. That's the kind of signal you get from a clock, from an oscillator, from something designed. Consider, if an advanced civilization wanted to send a signal across cosmological distances, they'd need enormous power, and they'd want a pattern that couldn't be mistaken for noise. A rhythmic pulse, like a heartbeat, would stand out against the random chaos of natural radio emissions. It would say, "This is intentional. This is not an accident." But then why only 3 seconds? Why only once? And why billions of light-years away, so far that any response would take billions of years to arrive? Unless, that's not the point. Unless the signal isn't for us. Unless it's a beacon, or a navigation aid, or communication between 2 points in space that happened to pass through Earth's line of sight. Or a funeral broadcast, the last transmission from a dying civilization sent billions of years ago, finally reaching us now. MIT astronomer Calvin Leung, part of the CHIME team, is cautious about the alien hypothesis. "We're looking at physics we don't fully understand," he says. "Before we invoke extraterrestrial intelligence, we need to rule out every possible natural explanation." And magnetars, with their extreme magnetic fields and occasional flares, remain the leading candidate. But the March 2025 RBF-LOTE discovery complicates everything. Because if RBF-LOTE is a one-off, and preliminary data suggests it is, then we have clear evidence that not all FRBs come from the same type of source. The repeaters like FRB 121102 and the periodic heartbeat of FRB 201912221A might be magnetars, but RB-FLOTE, with its single catastrophic burst, might be something else entirely. So here's what I genuinely want to know from you. After seeing the data, the heartbeat signal that flashed once and never repeated, the brightest burst ever detected that came from a galaxy we'd monitored for 7 years with no warning, what do you think we're actually detecting? Option A: natural astrophysical sources. Magnetars, pulsars, neutron star mergers. Physics we don't fully understand yet, but nothing alien. Option B: mixed phenomena. Some FRBs are natural, repeaters, but one-offs like RBFLOAT might be artificial signals or exotic physics we haven't discovered. Option C: all artificial. Every FRB is a technological signature. We're detecting an intergalactic communication network and don't yet recognize it for what it is. Drop your vote in the comments. Because this isn't academic speculation, CHIME detects FRBs almost daily now, and with new telescopes coming online, we'll soon be detecting thousands per month. If even a fraction of them are artificial, we're about to realize we're not alone. And if they're all natural, we're about to discover new physics that will rewrite our understanding of the universe. Here's why this matters beyond just one mysterious signal. Fast radio bursts could be used as cosmic probes. The radio waves travel through the intergalactic medium. the thin gas between galaxies, and gets slightly delayed by interactions with charged particles. By measuring this delay precisely, astronomers can actually weigh the universe, and they can detect the missing matter that should exist but hasn't been directly observed. FRBS are showing us the structure of space itself, and if they're periodic, if we can predict when and where they'll appear, they could be used as astrophysical clocks. As the universe expands, the frequency of the pulses would shift slightly. By measuring this shift over time, we could determine the exact rate of cosmic expansion, potentially resolving major disputes in cosmology about whether the universe is accelerating faster than models predict. But to use FRBS this way, we need to understand what they are. We need to catch more periodic signals. We need to determine whether sources like FRB 20191221A will ever flash again. And we need to figure out why some sources repeat thousands of times while others flash once and vanish. The KIME team, along with collaborators worldwide, continues monitoring the sky. Every day, Earth's rotation brings new regions into view. Every day, there's a chance another heartbeat will emerge from the darkness. And with the outriggers now operational, they can pinpoint sources to specific regions within galaxies, even to individual stars or star clusters. Future telescopes promise even more. The square-kilometre array, currently under construction in Australia and South Africa, will be 50 times more sensitive than any existing radio telescope. It will detect FRBS from the edges of the observable universe. It will capture thousands of bursts per day. And somewhere in that flood of data might be the answer. But we don't have to wait. Right now, as you watch this, CHIME is scanning the sky. And somewhere out there, in a galaxy billions of light-years away, something is preparing to flash. Maybe a magnetar's crust will crack. Maybe magnetic fields will snap and reconnect. Maybe a neutron star will collide with a companion. Or maybe something else entirely. Something designed. Something intentional. Something that has been pulsing its message into the void for 1 billion years, waiting for someone to finally hear. But fast radio bursts aren't the only mystery hiding in deep space. There's the WOW signal, the famous 1977 detection that has never been explained. There's Tabby's star, KIC 846852, which dims irregularly in ways that no natural explanation fully accounts for. And there are the vanishing stars, over 800 stars visible in the 1950s that have simply disappeared from modern surveys. And if you want to follow these cosmic mysteries as they unfold, as new bursts are detected, as patterns emerge, as we edge closer to an answer, subscribe. We're covering real-time astronomy, tracking signals from billions of light-years away, watching as the universe reveals whether we're alone or surrounded by voices we're only now learning to hear. On December 21st, 2019, something sent us a heartbeat. 14 pulses over 3 seconds, perfectly timed. More than 1 million times brighter than anything natural should be. From a galaxy so far away, the light left before Earth had complex life. And we don't know if it will ever speak again. The question isn't just what sent that signal. The question is, are we listening carefully enough to hear what it's trying to say?